In this video, we're going to go over section 5.1 from our textbook, which goes over antiderivatives and indefinite intervals. So we'll start with the definition of an antiderivative here. So a function capital F is an antiderivative of another function lowercase f if the derivative of capital F is equal to that function lowercase f. So for example here, this function x cubed over 3 is the antiderivative of this function x squared, because if we were to take the derivative of this guy here, we get our function. However, this function, capital F of x, is not the only antiderivative of x squared, right? And this is because if we were to take the derivative of this function here, we also get x squared. The derivative of this function here is also x squared, and same for this one. And this is because we know that the derivative of a constant is going to be 0. And these are all constants. So what we say is the antiderivative of x squared is going to be x cubed over 3 plus capital C for some real number c. And that is going to be the antiderivative of x squared, because if we were to take the derivative of this, we get x squared. So this brings us to theorem 1 here. It says if the derivatives of two functions are equal on an open interval, then the functions will differ by at most a constant. So, relating this to what we just looked at, these guys here, if we take the derivatives of all of these guys, we get our x squared function here, and we see that all of these guys only differ by at most a constant. So symbolically, if capital F and capital G are differentiable functions on some interval, and the derivative of f and g for all x in this interval, then f of x is going to be equal to g of x plus k for some constant k here. So let's look at some examples. This example here, we're told that the derivative of x cubed is equal to 3x squared. And the first thing we want to do is find all antiderivatives of f of x, which is equal to 3x squared. So, doing part A here, we know by the theorem we just looked at, so theorem 1, any antiderivative of our function f of x will have the following form. X cubed plus c. Okay, so we just saw that from theorem 1. So this expression here contains all of the antiderivatives of this function. Okay. Now for part B, we want to graph the antiderivative of this guy that passes through these points here. So first thing we have to notice, we want to graph the antiderivative that passes through this point. We're going to look at the antiderivative at that point. And so plugging in 0 into our antiderivative here, this implies that our function, when x is equal to 0, is just equal to c. Alright. And then we know that when we plug in 0 into our function, the output is going to be 0 as well. So this tells us that at this point here, f of 0 is going to be 0, and therefore c is going to be 0. Because we said f of 0 is equal to c, and we know that f of 0 is equal to 0 in this case. So this tells us that this function will pass through this point here. Similarly, we want to look at this point here, 0, 1. We already know from above that f of 0 is going to be equal to c. And so plugging in 0 into our function, what we'll get here is c here, and then we know, oh sorry, what we want to show in this case, we already know that f of 0 is equal to c, and we know that when we plug 0 into our function, it should output 1. So what this tells us is that c is equal to 1. So this tells us that our function becomes x cubed plus 1. And this guy will pass through our point 0, 1. All right, and then lastly, we're looking at the point 0, 2 here. And again, we're plugging in 0 to our function. We know when we plug 0 into our function, we're going to get c here. And in this case, it says when we plug in 0, we want to get 2. So f of 0 is going to be 2, which then implies c is equal to 2. And we can conclude that our function is going to be x cubed plus 2. That passes through the point 0, 2. And so we're going to color code these for the graph here, because the question asks us to graph it. All right, so what we have is the cubic function here. And as you can see, I've already graphed these guys. This is the cubic function that's passing through our origin, which is passing through this point. In this case, this is our cubic function, this green curve that passes through the point 0, 1. And in this case, we have the cubic function that passes through the point 0, 2. Okay. And then for part C, it asks how the graphs of these three antiderivatives are related. And it might be pretty obvious here, especially looking at the graph, but the graphs here are vertical translations of each other. All right, we can just see that by the different constant values in these functions. And so this example is meant to illustrate that these are all antiderivatives of each other that will just differ by one constant. All right, so this brings us to indefinite integrals, formulas and properties for these guys. So by theorem 1, we know that if the derivatives of two functions are equal, then the functions will differ by at most a constant. And what we'll do is we'll use this symbol here, called the indefinite integral, to represent the family of all antiderivatives of this function. Okay? So what this means is that this indefinite integral here represents the fact that the antiderivative of our function is going to be equal to this plus some constant c. And then just some facts about this guy. So this symbol here is going to be called the integral sign. The function f of x is called the integrand. And then the symbol dx here indicates that the antidifferentiation is performed with respect to our variable x. And lastly, c here is going to be called the constant of integration. And this is some arbitrary constant, as we saw in the last example. And so referring to the very first example we looked at, where we said x cubed over 3 plus c was the antiderivative of x squared, we can write it using our indefinite integral symbol, since again we said that the derivative of our antiderivative here is equal to our original function. And then just some facts, something to note here. The fact that the indefinite integration and differentiation are reverse operations, we can express this symbolically as taking the derivative of this indefinite integral here. They kind of just undo each other and we end up with our function. So this means the derivative of the indefinite integral of f of x is just f of x. Similarly, if we were to take the indefinite integral of the derivative of our function here, this is just going to be our function plus some constant c. Okay, so they're just undoing each other. All right, so next we're going to look at some formulas for indefinite integrals. So we're letting this capital C just be some constant, so that the integral of this guy here, so x to some power n with respect to x, is going to be equal to this guy here. So it's going to be x to the power n plus n over n plus n plus some constant c. And of course we can't divide by 0, so we know that n is not going to be equal to 0. Similarly, the integral of e to the x is just going to be e to the x plus c, because we know that if we were to take the derivative of this guy, we would just get e to the x. And lastly, the integral of 1 over x with respect to x is going to be ln of the absolute value of x plus some constant c, where x cannot be equal to 0. So remember the natural log, so ln, this natural log function is only defined for positive x here, so x cannot equal 0. But in this case, if we have the absolute value of x, it will be defined for all x, because we can plug in negative x values here, which will make this positive. The absolute value will make this positive. All right. A couple more properties here are that if we have some constant k, we would take the integral of some function times this constant k with respect to x, we can pull that constant out. So this means the indefinite integral of a constant times a function is the constant times the indefinite integral of our function. Okay. Similarly, we have this property here, and this tells us that the indefinite integral of the sum of two functions is going to be the sum of their indefinite integrals. Okay. And this also holds if we were looking at the difference. So the indefinite integral of the difference of two functions is the same as the difference of their indefinite integrals. Okay. A few other things to point out here. If we have that n is equal to 0 for formula 1 here, this guy here, we'll essentially have x to the power 0, which is just 1. So in this case, you'll take the indefinite integral of 1 with respect to x, and that'll just be x. Because we know that if we were to take the derivative of this guy, we take the derivative of this, we know the derivative of a constant is 0 and the derivative of x is 1, so we'll just get 1 here. Okay. So when we write this, we can kind of imagine like just an imaginary 1 there. All right, so then this tells us by property 4 here, if we have this constant k being multiplied by 1 here, this is the same as this guy being multiplied by this constant k. And then if we were to distribute this k to both terms here in the parentheses, we'll get k times x plus k times c, where c was our arbitrary constant. But notice that when we multiply this kc here, this will also be a constant. A constant times a constant is just a constant. So what we'll do is we'll replace it with a single symbol that will denote an arbitrary constant and write it in this terms here. All right. Now similarly, if we're using property 5 here, so we're looking at the sum or the integral of the sum of two functions here, we can split these guys up, and we have the integral of e to the x is going to be e to the x plus c1, and then the integral of 1 over x with respect to x is going to be ln of the absolute value of x plus c2. And we know that c1 plus c2, so constant plus a constant, is just going to result in another constant. So we'll replace it with just c here. All right, so that was a good amount of information. Let's see if we can apply it to some examples here. So looking at this problem, we want to evaluate each of these indefinite integrals. So we'll start with a here. So the integral of 2 dx. And so what we can do is pull this constant 2 out. So we're going to use property 4 here. So pulling this 2 out, we're now going to take the integral of dx here. And so we can think of this as having this imaginary 1 here. And so we know that if we take the integral of dx here, it's going to be x plus c. So this will be equal to 2 times x plus c here. So then we'll get 2x, and then remember, if we're multiplying this by a constant, we're still just going to get a constant, so we're just going to call that c. All right, looking at b now, we're going to take the integral of 16e to the t times dt, or with respect to dt. All right, so in this example now, this dt indicates that we're differentiating with respect to the variable t now. So we're going to do the same thing, we're just now differentiating with respect to t. So first we'll pull this 16 out here, and we want to take the integral of e to the t with respect to t. We know that the integral of this guy is just going to be e to the t plus c. We saw that up here. So this will become 16 times e to the t plus c, which will just be 16 e to the t plus c. Alright, let's do part c now. Looking at the integral of 3 times x to the 4th, and we're taking the integral with respect to x. Right? So again, we can pull this 3 out, and then take the integral of this function. Now what we'll use here is the first formula that we saw. So we're taking the integral of x to the power n. With respect to x, we're going to end up with x to the power n plus 1 over n plus 1 plus c. And so in this case, our n is 4. So this 3 is going to be on the outside, and it's going to be x to the n plus 1 over n plus 1 plus c. So what we'll get here, 3 is still on the outside, and we'll get x to the 5th over 5 plus c. And then lastly, we would just write that as our coefficient in front of our x to the 5th is 3 over 5. And so that'll be our answer there. Just going to box these so it's clear for each one. All right, let's look at part D now. We're taking the integral of this here with respect to x. So for this one, we'll use property 5 here. So remember, this says that if we want to take the sum, or the integral of the sum of two functions, that's the same thing as taking the sum of their integrals here. And same if we're looking at the difference of these functions. Okay. So we essentially can break these guys out into their own integrals. So we have the integral of 2x to the 5th with respect to x, minus, so we're taking the difference of this guy, integral of 3x squared with respect to x, plus the integral of 1. Alright, so what we can do here, this first guy, is we can pull this constant out, and we're left with this. And we'll do the same thing for this term here. So this 2 stays out front, and remember, this is going to be x to the power 5 plus 1 over 5 plus 1. So x to the 6 over 6. And this will be plus what I'm going to call c1. So we're taking the integral of this, so it's going to be this guy plus some constant. Then over here, we're going to have this minus 3 out front, and then it's going to be x to the power 2 plus 1. So x cubed over 2 plus 1, so 3. And then this is going to be plus c2. So when we take the integral of this guy, we're going to get this plus a constant. And lastly, we know from this first part here that if we're going to take the integral of this, we're going to get x plus a constant, which we're going to call c3. So simplifying this guy, here we can divide both of these guys by 2. So we'll get 1/3 times x to the 6. Then we're going to ignore this constant for a moment and look at this guy. These 3's cancel, so we just have minus x cubed. And we're going to ignore this for a moment and then just look at this x here. And the reason being is because we saw up here that if we have, this is the case, when we split out these integrals, we can just combine their constants into 1. So we'll just get plus c there. And so this is our answer for that one. Now let's look at part E. So we have, I'll put that on this page. We're looking at the integral of 5 over x minus 4 times e to the x with respect to x. So again, what we'll do is split this guy up. So this is going to be the integral of, and note that 5 over x is the same thing as 5 times 1 over x, so we'll use that as well. So we'll get 5 times 1 over x plus the integral of 4e to the x dx. Okay. So then we'll pull these constants out of both of these guys. All right, and then we saw from above that the integral of 1 over x is going to be ln x plus c. So for this guy, we'll get 5 times ln absolute value of x plus c. And then for this guy, we know the integral of e to the x is just e to the x plus c. So we'll get 4 times e to the x plus c. And then our last step is we'll combine these constants. So we'll get 5 times ln absolute value of x plus 4 times e to the x plus c. All right, so this will be, and sorry, I just realized that I, for some reason, added these guys, but we're subtracting this 4e to the x. Right, so when we're doing this, we can split out our integrals, but we are subtracting them because we're looking at the difference of these functions. Okay, so there should be a minus, and a minus, and this will be our final answer. All right, and then something else to note here is that you may have noticed in the first couple examples, I kept this constant out and I had it multiply the entire thing that we got for this integral here and then distribute to everything in here. Same for this guy here. I left this constant out on the outside, and then I had, I took the integral of this and had the constant multiply everything when we take the integral, including plus c here. And then I started to drop that notation, especially in these two examples here. And the reason being is because we know that when we distribute this constant here, we're just going to get a constant. So I'm only concerned with this constant multiplying this part of the integral, or this part of our answer when taking the integral. Okay, so here, for example, in part D, we don't have to have 2 being multiplied to everything that we get when we take this integral. We just have the 2 on the outside of this portion of it, because we know eventually we're just going to combine all of the constants into one big constant here. Okay. All right, let's look at a couple other examples here. For these guys, what we're going to have to do is just rewrite the functions a little bit. So let's look at this one here. We have the integral of 2x thirds minus 3 over x to the fourth dx. So for this one, we're just going to separate them. All right, and then what we can do is pull these constants out and rewrite these guys a little bit. So I'm pulling out this 2 here, so we're just going to look at the integral of x to the 2/3 minus, so what I'll do is I'll pull this 3 out, but I'm also going to rewrite this, because this will become 1 over x to the 4th, but I'm just going to rewrite this with negative exponents. So we're looking at the integral of x to the negative 4 dx. All right. Now taking the integral, we have 2 on the outside here. And this is going to be x to the n plus 1 over n plus 1 plus c. So we're going to have x to the 2/3 plus 1, which is going to be 5/3, over 2/3 plus 1, which is 5/3, and then plus c1 here. And like I just mentioned at the end of the last problem, I'm not concerned with keeping this c1 in these parentheses so that this 2 can distribute to both of these guys, because in the end we're just going to end up with an arbitrary constant anyway. All right. Then for this guy here, we're going to have minus 3. And then we're going to have x to the n plus 1 over n plus 1. And in this case, n is negative 4. So this will be x to the negative 4 plus 1. So that'll be x to the negative 3 over negative 3 plus c2. All right, so let's simplify this a little bit. In this case here, if we're dividing by this fraction, that's the same thing as multiplying by its reciprocal. So 3 over 5 here. And then here we have these negative 3's cancel and make this a plus. And so we'll have plus x to the minus 3 plus c2. All right. And then we can multiply this 3/5 times this 2 here. So we'll get 6 over 5 times x to the 5/3 plus x to the negative 3, which actually we'll write with positive exponents, so this will be 1 over x cubed. And then we'll combine these constants into one big guy. And so this will be our final answer here. All right, now for part B, we're going to have to do some algebraic manipulation to write this in a better form to take the interval. So we have the integral of 4 times the 5th root of w cubed. And we're taking this integral with respect to w. Right. So again, the first thing we'll do is pull this constant out. And then remember, when we have something of this form, this is the same as three over 5 here. Right? Because remember, if we have the nth root of something, that's the same thing as that thing raised to the 1 over nth power. Okay. So that's where that comes from. So taking the integral of this, it'll be w to the n plus 1 over n plus 1. In this case, n is 3/5. So it'll be w to the 3 over 5 plus 1, which is 8 over 5, over 8 over 5, plus c. So then this is the same as w to the 8 over 5 times 5 over 8. And then we'll divide this by 4 and this by 4. And so we'll end up with pulling this 5 into the front. 5 over 2 times w to the 8 over 5 plus some constant c. All right. And then for the last problem, we're going to have to rewrite this guy a little nicer too to take the integral. So we have the integral of x to the 4th minus 8x cubed all over x squared dx. Okay, so for this case, we can just simplify this guy. We see that we have an x squared in every single term here, so taking out an x squared from every single term, we'll get 1 on the bottom. So we'll get x squared minus 8x. Okay, so now we can take the integral of the difference of these functions by splitting them up. I'll also pull this 8 out in the front. And so we get that there. So then in this case, taking the integral of this, so it would be x to the 2 plus 1 over 2 plus 1. So x cubed over 3 plus c. And then here, our n is going to be 1, so it's going to be x to the 1 plus 1 over 1 plus 1. So x squared over 2 plus c. So then we'll get 1/3 x cubed minus, we'll get 4x squared plus some constant c. All right, so now we'll look at some application problems. First, so we want to find the equation of the curve that'll pass through this point if the slope of the curve is given by this at any point x. So essentially what this is saying is that we want to find a function y such that dy dx is equal to 3x squared, and when we have that x is equal to 2, our output is equal to 6, so y is equal to 6, or f of x is equal to 6. F of 2 would be equal to 6. All right, so we can find our y by using the properties of integration. We know that the integral of this dy dx is just going to be y. Right? We saw that earlier. So this tells us that to find this function here, we'll just take the integral of this guy here, of 3x squared, with respect to x. So what we'll do is we'll pull this constant out, and then take the integral of x squared. We know that this is going to be x to the 2 plus 1 over 2 plus 1, so x cubed over 3, plus some constant c. So simplifying this, we'll get 1 over x cubed, we'll just get x cubed plus c. All right, and then what we'll do here is use this point to find our value for c. So we'll use the fact that x is equal to 2, or that y is equal to 6 when x is equal to 2, to find c. So what I mean is, when we plug in 2 to this guy here, right, because our f of x was equal to this guy, we'll get 2 cubed plus c, and we know that this has to be equal to 6. So this tells us that 8 plus c is equal to 6, and then solving for c, we'll get that it's equal to negative 2. And then once we have our value for c, we'll plug that into our equation that we got here. So y is going to be equal to x cubed minus 2. All right, we'll look at one more problem here. We want to find the revenue function, r of x, when the marginal revenue is given by this here, and when no revenue will result and no revenue results when we have a 0 production level. And then we also want to figure out what is the revenue at a production level of 1,000 units. So essentially what this is saying is we know we want to find our revenue function, r of x, given the fact that r of 0 is going to be equal to 0. When x is equal to 0, so when we have 0 production, our revenue will be 0. All right, well, we know that if we want to find r of x, we're just going to have to take the integral of r prime of x, of our marginal revenue. So this will be equal to the integral of 400 minus 0.4x with respect to x. So splitting these guys up, taking the integral of 400 minus the integral of 0.4x. We know that if we were to pull this 400 out, we're just going to get the integral of 1 dx, which we know is x, and then we're going to multiply that by the constant that we took out, which is 400. So I'm just going to write 400x here, and we know that's going to be plus c. Okay. Similarly, on this side, we know that we can pull this constant out. So I'm just going to write that there, and then we'll look at the integral of just this x here. This is x to the power 1, so n is 1 here. So it'll be x to the 1 plus 1, so x squared over 2. And then plus some constant c. Alright, so simplifying this guy a little bit, we'll get 400x minus 0.2x squared plus c. Alright, so this will be equal to our revenue function. And so what we're going to do is use this here, or this here, to find our value for C. So plugging 0 into our function we just found, we'll get that C is equal to 0. Because R of 0 is equal to 0, and then these guys all go to 0. So C is equal to 0, and therefore R of x, our revenue function, is going to be 400x minus 0.2x squared. Alright, and then the last part of the question, we want to figure out the revenue at a production level of 1,000 units. So we'll just plug in 1,000 into our revenue function. Doing so, we should get 200,000. Alright, so that'll be it for this video.